Okay, good morning everyone. Welcome to Artificial Life and Evolutionary Algorithms special track from EPIA. This is the 6th edition of this special track. It started back in 2003 in the EPIA that took place in Beja. And throughout this day we will have 3 sessions with a total of 9 papers. The first speaker is Rui Antunes, and he will present a paper about the agent storytellers in Where is Lourenço Marques. So, go ahead. You know, you have 25 minutes of press, please.
Thank you. Yeah, so as Fernando said, so my name is Rui Filipe Antunes, and I'm a visual artist doing a PhD in these themes of art and evolutionary art and digital art and in artificial intelligence applied at Goldsmiths, University of London. And the work I'm going to present is I'm going to talk about the artificial intelligence in an artwork called Where is Lourenço Marques, which instead of boring you with my speech, I'm going just to quickly show us a quick video about the motivations.
Historical period of Portuguese domination. The elaboration of the project started from a process of interviews with the community who left that city during the period next to the independence in 1975 and now lives in Portugal. Their accounts and shared material form a memorabilia from which an artistic and subjective reconstruction of the city was built in a 3D environment. Community of humanoid avatars functions as agent storytellers. They roam autonomously the city and interact with each other as well as with the human audience. When the user selects any of these avatars, it interrupts its current activity, then, animated and gesticulating as if they were speaking, each of the individuals in this population is the bearer of an excerpt from an interview, functioning as the carrier and mediator of real-life human stories. The audience is thus implicitly invited to seek out these storytellers, chasing virtual characters through the city in order to listen to their stories. The more
Sorry. So, because this is my speak, so that's precisely what we're going to talk is about the model of intelligence that is behind the storytellers. So this is, as you understood from the video, is a work that has a representation online. It's a virtual world that you can access. I'm going to give details about that in a second, and also is exhibited in galleries, which was quite good in terms of feedback. So there is a second version, which I'm not going to talk unless we have time in the end, which was built upon comments that were produced. So, yeah, this is quite complex. There is the construction of the virtual world has many layers. There is a paper on Leonardo that was published last year about this. It's quite intricate and complex because it deals with the issues of representation, post-colonialism, ethnography, and so on, which I'm not going to bother you with that. What we're going to talk is about this top layer of the storytellers. So the community of agents that transmit the accounts from the interviewers. No, sorry, the interviews. Kenneth Stanley was brilliant because it saved me a lot of work in terms of these introductions, especially in terms of providing this framework where stepping stones are required. So I'm going to introduce some basic stepping stones which are fundamental to build the framework of that informs this paper or this work. Probably all of you know, so what is evolutionary art, but in case you don't know, is what Peak Breeder was about. It's about evolving images or evolving things, because it's not restricted to images, but so basically what he gave this brilliant concept of function composition. So the first paradigm of evolutionary art is about having a G-type that is converted into a P-type. A G-type is some form of DNA, a blueprint that encodes the image, and then there is a process of translation of that G-type, of that blueprint, into phenotypic features. This process of translation is a linguistic process. So there are symbols, and there are interpretation of those symbols. So there is two levels, a syntactic level and a semantic level. This is important, you'll see in a minute. This is one of the fundamental stepping stones. So this is, as I say, this is the first paradigm of evolutionary art. The second is when this principle is applied to communities of agents, which typically are organized in food chains. So one's eat the other, so they're trading, they're competing for space and usually for some form of currency, usually in terms of energy. So one's eat the others. The third paradigm, I argue, is happening geographically situated in mostly in Monash University in Australia, where it's not the individuals who are the important bit, but what they're doing, their internal states. And so these guys are using it to produce soundscapes based on the dynamics of the community. I'll illustrate that. Imagine that we are in Rome, in an arena, we have lions, we have gladiators. So this is a computational ecosystem. So ones are eating the others, are competing for survival. And imagine that we have a chorus, that every time a gladiator gets on stage, they sing la 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 la. Every time a lion gets on stage, they sing do 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 do. And every time a lion eats the gladiator, they sing si 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 si. Okay, so this produces the dynamics of what is happening on the ecosystem is producing this soundscape. Okay, so it's not the individuals themselves, but what is happening. I'm not going to. So let's quickly make an exercise of imagination and imagine that we have on the same arena in Rome. Two journalists that are reporting everything that is happening. They need to write really fast because events are happening on real time. So they use that code over there in the right corner to write things like this. So L1, lion 1, which is at coordinate 510 of the arena, moves to coordinate 1020, where the gladiator 3 is. Of course, they know what does this mean because they have this Rosetta Stone. They know that M means move, the L means lion. In the airplane, I've lost some slides, so I don't know what happened afterwards. What I know is that piece of that document that the journalists have written appear in London later, some centuries later, in a boot sale. A boot sale is Feira da Ladra. Amongst things that seem to belong to a context of dance, and there is this young choreographer that passes by, and he gets ecstatic because this they seems to be the belongings of this famous choreographer that passed some years ago. And he was working on a famous piece. And so imagine that this piece of paper that he found is that lost piece, that lost dance piece, because he has he has no Rosetta Stone. So what he imagines is that the M that we saw, that we know that was the move, he imagines that M is this specific dance movement, and so on. So the actions that are produced by the lions eating the gladiators is translated into a dance piece. This was catastrophic. The result was catastrophic. The choreographer ran away. He'll never tried anything better afterwards. But so I wrote down after. So I picked this and wrote this paper, which is important because it shows that if we detach the narrative, remember that in the beginning I said the first paradigm of evolutionary art is a syntactic element that is converted into a semantic element. So there is a process of interpretation. So if we remove this process of interpretation, or we switch it, and detach the narratives of life that computational ecosystems have attached, what the computational ecosystem is a generative engine for heterogeneity, spontaneity, and novelty. So this is the merit of this paper, and this is where we depart from, where is Lawrence Marx. By the way, this is the address for the online version. There is a forum and there is a survey, so please add some comments on the survey. It would be nice if you visit. So the principle for animating these characters, in Where is Lawrence Marx, is precisely to detach this literal translation of the actions that are happening in real time in the ecosystem. So instead of seeing a lion running to a gladiator, what we see is a predefined animation of a guy talking. So this will be an attack, this will be a defense, this will be I want to get close to you, I'm trying to find someone, but I cannot find in my range, and so on. So there is a set of predefined animations that are coupled with the actions that are happening on the ecosystem. In order to implement the agency model, I drew on a basic on existing work. So I didn't invent anything. I just put them together in some efficient strategies. So each individual is defined by a G-type, so a series of a bit string composed of ones and zeros, and then based on Sarwatari and all, each individual has chemicals, so a portion of that string defines the chemical composition of that particular individual, and then another section defines what chemicals can this individual digest, and based on this, a food chain emerges. And Sarwatari and all, they've proven that this is quite efficient, and it generates food chains up to 15 trophic levels. Then another section of the bit of the G-type codifies a set of hormones. This is based on Daniel Jones, 2007. His work is for swarms, but basically is a set of variables which are mimicking human hormones. So they change throughout the day, they affect each other, and so these are the internal sensors. So the model itself is quite simple. It's the typical sensors, decision and actuators. So we have the hormones feeding in the system, and also we have a sensor of touch. And then we have a classifier system, which is John Holland and John McCormack. So John McCormack drew on John Holland, and I'm drawing on both of them. So the classifier decides what actions are going to be taken. These are performed, and then these are rewarded according to the consequences that they have in the system. Say, one individual wants to eat, he finds a prey, so this will be positively rewarded. I'm sure that you know this kind of systems. So results. On the bottom, what we have is each frame is 15 minutes of run, with the spatial distribution. So where is each individual? So it just supposes 15 minutes of location. So this is probably one individual moving. So every 30 seconds there is a snapshot. And as you can see, what we see is that it's far from random, the distribution. And it changes throughout time, and it changes throughout, from run to run. So this is an emergent behavior, which is quite interesting for the purpose of animating a space. And on top, what you see is the behaviors generated. As you can see again, it's far from random, and the two top columns, what they are the behaviors that have been mostly triggered, so the more common. And so one is attempt to find a reproductive partner, this one, and then reproduction is quite lower compared. And the other main behavior is being hungry. So they're always hungry and trying to basically trying to find the reproductive partner. But again, there's a quite divergence between the intentions and the effective consequences. And I would like to thank my sponsors, Fundação para a Ciência e Tecnologia and Fundação Telefónica, which sponsor this work. Any questions?
So we have time for questions. Okay, I have one or two questions that I would like you to try to explain it. Well, it seems to me that the behavior of the agents is defined by the classifier system that you showed us. So how does this classifier system evolves over time? So when they generate a new avatar, does it changes? Is it modified? So
I was afraid that you would ask this because it's quite it becomes complex. I will try to explain briefly. So we have the sensors, and each sensor generates one message of urgency, say. So imagine I'm being touched. So this increases. It starts incrementing that the touch message, and so from time to time, a priority. So we get the higher ranked urgency. Let's call it like that, and this message is going to be matched against a rule table. What these rule tables have is actions. So these animations that we talked about before, and this is where the evolutionary part or process happens. So sometimes, from times to times, sorry, I forgot to mention this. So remember that I said the actions are rewarded according to the actions, the effects that these actions produce in the world for the agent. So this gives a priority for each rule. So from times to times, we pick. I'm not sure entirely, but it's the first, and I think is third or something like that, and we cross over, we reproduce them. So we don't generate new rules in the context of evolutionary, in an evolutionary context, but what we do is we reshuffle the actions.
How are these rewards defined? So you say that actions are rewarded, so you predefine which actions are rewarded? And is it an immediate thing? So they do something and they immediately get a reward?
So there is a so who defines this is it was my decision.
Maybe it will help you to in your comment. When I ask you this, my question is, well, if you completely define which actions will be rewarded and what the reward will be, so don't you risk that your agents will end up doing exactly what you told them to do? So is there any novelty in their behavior?
No, what can you yeah, you can. No, in that respect you're right. What happens is, what I'm interested is in noise. So I want to eat you, but I don't do it immediately. So because other things will happen in between. So it's like I'm hungry, but now I'm in the conference, so I need to wait. Somehow it's this type of noise that I'm interested in generating between.
So there is a chain of events before a reward eventually appears.
Yeah, okay. Effectively. And then there is a memory. So there are the previous 5 actions that led to this reward are also rewarded in a decreasing order.
Okay. Do the agents interact with each other apart from reproduction? Is there any kind of interaction? Do they change their behavior when they are moving in the environment?
I will show you the video in a second. Yes, so basically they're supposed to mimic talking. Let me.
During the historical period of Portuguese domination,
Let me see, I don't know. Yeah, this type of.
Okay.
The paper shows a URL video for this, that illustrates this better, and of course you can. So, of course you can always go to the online and check that out. But basically, the idea is that they aggregate talking to each other. So we don't see them eating each other, but they're trading energy, or they're reproducing, or they. So the idea was create this simulated human behavior, where some they walk past, some they pass and they go to their objectives, and some they stop and have a chat and move on.
Okay, thank you. So we still have time for one more question. Okay, so no more questions. Let's thank our speaker.
Thank you. No, thank you.
Okay, and now we'll move to the last speaker of this session, Leonardo Vaneschi, and he's presenting a paper with a really long title. Let me try to read it. An efficient implementation of geometric semantic genetic programming for anticoagulation level prediction in pharmacogenetics. Is that it? Okay.
Can you hear me? Okay, thank you. It doesn't work. It works. If you don't plug it, it doesn't work. Anyway, thank you very much. My name is Leonardo Vanneschi. It's a real pleasure for me to be here. And today I'm going to present you a very specific biological application of a new flavor and very promising flavor of genetic programming. So besides the biological application, which I will describe in the second part of my talk, I guess the real and important objective of this paper is presenting you, and this presentation is presenting you this new flavor of genetic programming, and in particular these recently defined geometric semantic operators for genetic programming, which are operators that we believe, and we have arguments to say, that are particularly effective. And so I will try to convince you of the goodness of these operators. In particular, I will show you how these operators can be used on this application that is actually a complex real-life application. And in particular, I will describe the behavior of the operators, both on training and testing data. Can you still hear me? Yes. Okay. Before beginning all this, I need to start with a little and very simple foreword, okay? Which is the presentation of a very simple optimization problem that could be solved, for instance, with GAs, okay, with a simple GA. And the problem is this. The solutions, the search space, are vectors of a prefixed length of real numbers. The fitness is the distance, and it applies to any distance measure, to a unique and known global optimum. So we are, of course, talking about a theoretical problem, because in practice the optimum is not known, but here we assume that it is known. And as genetic operator, we use something that I call, I'm not the first one, Ball mutation, which is the weak perturbation of some of the coordinates of an individual. Okay. You should be convinced before going on that every solution that is not the global optimum has at least one neighbor, which is the solution obtained by means of a mutation, which has better fitness, which means that in this problem there are no local optima, okay? And the fitness landscape is unimodal. Example, you take one solution, which is one vector of real numbers, you know the global optimum, its fitness is its distance, with any distance measure, to the global optimum. It is always possible, if the individual is not the global optimum itself, to do something like this. Weak perturbation of the coordinates, even though it is not true that every coordinate goes in the direction of the global optimum, the global distance is smaller to the global optimum, and it is possible, always possible to do it. So the definition of a local optimum is the best individual in the neighborhood. Here, this is not possible unless the individual is the global optimum, so there are no local and non-global optima. So this problem is easy to solve for every heuristic, including the simple hill climbing. Okay? Do we all agree on this, which is actually very simple? It does not make sense to go on, but I think we can all agree on this. Okay? This is the basis of what I'm going to say next. So now it seems that I'm slightly changing subject, but I'm not. Okay, I will go back here. Genetic programming can be seen as, or is, in many senses, a machine learning method for supervised learning. Okay, so I could present GP as a tool in which what is known is a data set composed by a prefixed set of input data and output data. The output data are known because it is supervised learning. What we look for is the function that interpolates the data. Okay. We could identify each individual, whatever it is, generally a function or an expression, with a vector that is the vector of the outputs on every input data. And normally the fitness is measured by means of a distance measure between the output and the target vector. Okay. In many recent contributions, among which this one, which is particularly interesting, this vector of the output is called semantic. And I will use this terminology in this presentation from now on. So from now on, the semantic of an individual in GP is the vector of its output values on the input data, on training data, which makes more or less sense because it is a coding of what the individual does on the data that we have. So it's semantic. In some senses, it makes sense. Let's consider a particular case of supervised learning, which is regression, which is particularly interesting for many applications. In case of regression, individuals can be represented by the output vector, which is a vector of real numbers. Okay? And given that we are in supervised learning, the target is known, and it is another vector of real numbers. Okay? So we are in a situation that is very similar to the previous GA problem. Okay? In some senses, what we miss is something that emulates ball mutation to get to a situation in which we are exactly in the same problem. So the real objective of this paper, of these operators, is to answer to this question, okay? Is it possible to define some modifications on the structure, on the syntactic structure of the individuals that correspond to some particular operators on the semantic space? For instance, it is possible to invent a modification on the trees, on the tree structures, on the syntax of the individuals that corresponds to ball mutation on the semantic space. Basically, what we want is this, okay? We can think about the world of syntax in which individuals are trees, and the world of semantic, which is a Cartesian space, okay? In which individuals are represented by a point, a vector of real numbers. Is it possible to invent something to modify the syntax such that the semantic of this guy is the semantic of the previous guy with ball mutation, with some small perturbations of the coordinates? At the same time, we are also interested in finding the equivalent in the syntax of a particular crossover called geometric crossover. So is it possible to create a recombination on the syntax of the individuals whose offspring has a semantic which stands in the segment joining the semantic, the 2 points of the parents? That's what a geometric crossover does. If we are able to find the first transformation on the syntax, the one that corresponds on ball mutation, then any regression problem, independently on how complex the dataset is, has a unimodal error surface, has a unimodal fitness landscape. We are mapping any regression problem to the previous and simple and theoretical GA problem, okay? Which means that, at least in principle, any regression problem should be easy to evolve for GP. At the same time, if we are able to find a transformation that corresponds on the semantic space to geometric crossover, then we are able to ensure, which is a property of geometric crossover in GAs, that the offspring is none worse than the worst of its parents. It is easy to convince oneself of this from this picture. The offspring, given that the fitness is distance to the target in the semantic space, the offspring is closer to T than this parent, okay? It is easy to see it in this picture, and it is possible to prove that this property is general. These would be extremely important results, right? For instance, if I have to refer to the invited talk of some minutes ago, it would not make sense to search for novelty anymore, because the fitness would be unimodal. So it would make fitness very useful and high evolvability for every single problem, once again, independently from how complex the dataset is. A very, very important objective, which in some senses we could ask if it's a dream or not, and in many senses it is, but it is turning into reality after the publication, very recent, of this paper, which is very important for us, published in PPSN 2012. by Alberto Moraglio, Kraviec, and Colin Johnson. In this paper, exactly operators with those properties have been defined, although with one important drawback, of which I will talk later. So now I'm quoting the paper of Moraglio and co-workers to describe how these operators work. And like in many cases when something important is discovered, you realize that the discovery is very simple, right? And these operators are actually very simple. So this is crossover. This is the crossover between two parents, T1 and T2, okay? And this is the expression of the offspring. This is the offspring, the unique offspring. TR is a random tree whose codomain, a random function whose codomain stands between 0 and 1. So what we are doing is a linear combination of T1 and T2 with coefficients between 0 and 1 whose sum is 1. So we are actually doing betweenness in the semantic space. This is a geometric crossover in the semantic space. The semantic of this guy stands between the semantic of T1 and the semantic of T2. Stands in the segment joining those two semantics. And mutation is this. This is the mutation of 3T. T is the parent, this is the offspring. TR1 and TR2 are two random functions. So what is the idea? We are considering the difference between two random functions, which is supposed to be a random function centered in 0. So a possibly small random function. And the importance of the modification that we do is can be tuned by tuning a constant, a numeric constant, which we call mutation step. It is maybe important at this step, at this point, to hint, we can discuss it later in the question time if you want, that is important the fact that here we have to put random expressions and not random constants, okay? Otherwise we would modify each coordinate of the semantic space of the same amount. We would not do ball mutation, we would do circumference mutation. That is not what we want. So we need something that has a different value on every fitness case without using data. And the only way that we have found is to use expressions, functions. So this is clearly a slight perturbation of the coordinates of T. Okay, the semantic of this is ball mutation of T, of the semantic of T. The problem, these operators work well, okay, and they have been proven effective on some benchmarks, okay, but they have this drawback, which is very important. Every time that you build the offspring, you have to use both parents, for instance in the crossover, plus another tree, use it twice, plus some symbols, some operators, some constants. And an analogous thing holds for mutation. So offspring are by construction larger, much larger than parents, which implies, in particular if you use crossover, an exponential growth in the size of the individuals. This makes these operators useless in practice. Yeah, after few generations, you are in a situation in which the individuals in the population are so big that you cannot evaluate the fitness, you cannot use them, okay? They are actually unusable. The solution that Moraglio and co-workers propose in their paper of PPSN 2012 is interesting but complicated at the same time. It is to introduce into the algorithm a phase of simplification, which means I take the offspring of any of the two operators, I give it as input to an automatic simplificator of expressions, and the output, which should be a function with the same semantic but possibly smaller, is what is going to go into the new population. Okay, we have to try more this method. Okay, we have tried a little bit, and we have seen that it is very, very complicated. Okay, for instance, we have tried Mathematica, which has an automatic simplificator of expressions, and Mathematica, if you give as input x plus x plus x, can output in few milliseconds 3 times x, right? But if you give thousands of nodes, an expression which is huge, also with arithmetic operators, it has problems. If you give even very simple expressions with the division, has problems. If you give if you use operators more complicated, like trigonometric operators, logarithms, and so on, very, very often the output is the same as the input. It is not simplifying, okay? So this method is interesting, deserves more investigation, but has a lot of problems, is at least very hard. So we propose here, and this is our contribution, a new implementation of the operators of Moraglio, which does not imply any simplification phase, and that are very efficient, and that make GP very efficient. And this is what I'm going to present to you, and this is actually the main contribution of this paper. The second contribution is the application to a significant real-life application. So how does it work, this implementation? The algorithm is the following. We begin with storing the trees of the initial population exactly as in standard GP. So we store in memory the tree structure of the trees of the initial population. Then we create a bunch of random trees that we will need to apply the operators. Okay? Both operators require the use of random trees, so we create them and we store them in memory. Then, when we store the next population, instead of storing the trees, we store something like this, okay? We suppose in this very simple example that we are using only crossover, but if we use also mutation, the thing is analogous. These are memory reference to the ancestors, okay? So these points here, these points here, these points here. So the next population is memorized by a field which is binary, either crossover or mutation, and 3 memory references. So something very, very small, okay? We don't need anything else, because once we know what is the operator and which are the ancestors, we are perfectly able to reconstruct, in a second time, the tree. The truth, which is what actually makes the implementation so efficient, is that we are also storing the semantics of all the trees that we have, of all the individuals that we have. So we are storing for each one of the initial trees the semantic, which is a vector of real numbers, and we are storing, when we construct the new population, also the semantic of the individuals of the new population, which is very, very fast, because we just have to apply the formula of the genetic operator to the vector of semantic of the ancestors, okay? So it is an operation which is very, very fast, and this occasionally makes the calculation of fitness very, very efficient, because you only have to make the distance between this and the target, which is very, very efficient. And even more importantly, fitness from now on is independent from the size of the individuals, which is quite unusual in GP, right? And that's what makes this implementation so fast. Let's try to make another generation in order to explain better how the algorithm works. Before passing to the next generation, it is typical that some of the genetic material of the previous one will not be used anymore. So we can delete it from memory by saving some memory. And then we do exactly the same thing, okay? We create another bunch to this table. We add another piece to this table. Once again, only pointers are here. Pointers to things that are in memory, okay? About the random trees, you can choose. You can, if you have memory, create others, or reuse the random trees that you already have in memory. So once again, this table grows, but this table is only memory pointers. So it is very, very non-expensive, cheap to memorize this table. Once again, before passing to the next generation, we can simplify, delete some parts of the memory that is not used anymore, and so on and so forth. It is possible to show, and we do it in the paper, that the computational cost of evolving a population of n individuals for g generations is linear in n and g, is O n times g. This is not so impressive, right, to see an expression like this. Probably something that is more impressive to convince oneself about the efficiency of the algorithm is what I'm going to show here, which is a video in which I am showing the evolution of standard GP, which is GP that uses the COSA traditional crossover and mutation, and geometric semantic GP, which is GP that uses only geometric semantic crossover and mutation. It is a real-time video, and the curve of standard GP is accelerated of a factor 10. Okay, this is a training test and this is test set, but don't care about the quality of the fitness by now, only about the speed. Okay, we will talk about the quality later. So this is what's happening. The red curve is geometric semantic GP. You can see how faster it is. Please remember that standard GP, this green curve, is accelerated of a factor 10. What is most amazing is that the green curves becomes slower and slower as the evolution goes on, because standard GP is bloating and the calculation of fitness depends on the size, while on the case of geometric semantic GP, this is not happening. It was not supposed to stop. I don't know it did stop, why it did stop. Okay, let's see it again. Maybe this time it will not stop. Maybe I've touched something in the remote that I was not supposed to stop. Anyway, you see the green curve slowing down because the calculation of fitness becomes more and more expensive, which is not the case for the red curve. Okay, and you can see a very, very big difference in the speed of these two algorithms. We have a last step to do, which is expensive and was not included in the previous video, okay, which is important. At the end of the run, we have to reconstruct the trees. We only have a bunch of pointers which are not so expressive. We have to reconstruct trees. The trees are huge, of course, because we are not doing any simplification, but this time, typically we are interested in just one individual, which is the best on training at the end, so we can just reconstruct one individual instead of doing it for every individual during the run. And even more importantly, we can do it offline without speeding the evolution. So our idea is we are looking for something. We don't even know if we are able to find that something. First of all, let's look for it as quick as possible, and then offline in a second time we will try to reconstruct it. Okay. This is in principle much faster than what the original version of geometric semantic GP did, okay, which was storing all the trees every time. So we have applied this new GP to this real-life application, which is the prediction of the appropriate dose of oral anticoagulant drug. We have collected the real data set of real data with real patients. So we are in collaboration with people that works in the medical field. The data set, it is a regression problem, okay? The data set is made like this. Each observation represents a patient, and each observation is composed by 32 features, which are particular features of the patients, which can be classified into these particular 5 classes. It is not so interesting in this phase. We have, in the dataset that we have used, 406 patients, so 406 different observations. They have been obtained after a cleaning phase. In a first phase, we had more than 700 patients. Some of them had information incomplete, some of them uncertain information, and so on. After this cleaning phase, these 406 patients have all the information they need. So the dataset is complete and reliable. And the target is the successful dose of this particular medication, which is one of the most known anticoagulation medications, one of the most effective drugs for oral anticoagulation therapy, used, for instance, in the prevention of thrombosis, embolism, and some other diseases of this kind. So the experimental results that we have can be summarized by these plots. This column represents training set, this test set. This is the best on training evaluated on the test set. We can see that, as expected, geometric semantic GP works better than standard GP on training data. It is expected because fitness landscape is unimodal. What was not expected was this. Okay, it works better than standard GP also on testing data, and what we were expecting was the other way around. We are working so well on training data, probably we are overfitting, right? It seems that we are not. And there is a statistically significant difference between the two versions of GP, both on training and testing data. Now we are interested in understanding why it works so well on testing data, okay? First of all, we wanted to see if this was a particular case for this data set. So we have done two things. First of all, we have done something that we cannot do for standard GP. For standard GP and for semantic GP, we have stopped at generation 500. For geometric semantic GP, we can go until generation 1000. So we have done this, okay? And we have seen that training set continues to optimize smoothly, which was expected, once again, because the fitness landscape is unimodal. But practically, there is no overfitting, right? See how irregular is the behavior on the test set of standard GP, and here you have a slight worsening of fitness on testing data, but not so irregular as for standard GP. And then we have done something else. We have tested it on other data sets of completely different nature. And here is, in all these plots, the black curve will be geometric semantic GP, and the gray standard GP. Here is dataset 1. See how irregular is standard GP. See how regular is on testing data. Geometric semantic GP, dataset 1, dataset 2, slight overfitting, but still nothing comparable to standard GP, dataset 3, dataset 4, dataset 5, and so on. I could go on. Okay, we have results on many, many data. So the trend is general. The trend is not for our particular data set. And these data sets have more or less the same complexity, even more complex than the one of our application that we are interested in. So now we can try to answer this question. Why? Okay, the trend seems general, so why it works so well on testing data? Okay, and our interpretation is the following one. Here we have the target on training data, okay, and we have this property of crossover that the offspring is not worse than the worst of the parents, okay. And now the difficult thing to understand and to convince is that we don't know where the target on the test set is, because we don't know the test set at training time, but we know it exists, and wherever it is, the geometric properties go on holding, okay? So we always have also on the test set an offspring that is not worse than the worst of the parents on the test set, okay? So basically we are automatically controlling overfitting. We are not guaranteeing, of course, that every time we apply our new operators we are improving on the test set, but at least we are guaranteeing that if we worsen fitness on the test set, this worsening is limited. And it is limited by a quantity that we can measure very well. That is the fitness on test data of the worst of the parents for crossover, and this mutation step, MS, for mutation. Okay? So we are limiting overfitness automatically by using these operators. It was not so obvious in the first definition of the operators, where we could not use them on real-life applications. And after our implementation, we could use it on real-life applications, and we could discover this very interesting property of controlling automatically the overfitting of these operators. So basically, we have our contributions are an efficient implementation of these operators, good results on this application, which is important, okay, which is significant, and the new insights about the generalization ability of these operators. We have these important open issues that are the fact that the reconstruction of the best individual at the end of the run is an issue, okay, is a problem, because the individual is still huge, okay. In many cases, it is even impossible to reconstruct completely the structure, which turns GP into something that I don't want to call exactly a black box optimization algorithm, because we know something about the final model. We know the bricks, we know the features used, we know the operators used, but we still cannot reconstruct the global, the total model, so let's call it a dark gray optimization algorithm. We are working on this, okay? We are trying to develop new operators with the same geometric properties on the semantic space, which do not create offspring that are so big. All these will be developed in this project, which is beginning in September of this year. So exactly in these days, it has been financed by the FCT, Fundação para a Tecnologia e Ciência. It is called MassGP. In this project, we will try to solve problems of completely different nature. There will be problems of maritime safety and security, but using exactly this version of GP or the new operators we will be able to define. Thank you very much.
So we have time for a few questions. Okay, maybe I can ask you just two small comments. Picking up your last observation, do you already have any clear idea on how to simplify the individual that you generate at the end of the run? That's my first comment. And the second is there any idea on how to generalize this approach to GP, which is not based on trees? Is any work on it?
About the first question, actually the true answer is no, but in EuroGP this year, I have seen a very interesting presentation by Menjit Zhang or Meng Zhang, I don't know exactly what is the pronunciation of his name, proposing basically pruning of trees. And the pruning in that application was particularly interesting for us because it was incremental. It was doing while the tree was built, okay? So it didn't have the large tree and then the simplification, which would be impossible for us. But while he was building the tree, starting from, I don't remember top down or bottom up, but starting from the leaf or from the roof or from the root, it was simplifying. And this is what we need, okay? So yes. I have to read and study better the paper, but probably we can do something about that. About the second point, should be the same, right? Should be the same. If you have arithmetics, even if the representation is linear, you have to do the first expression plus the second with some coefficients multiplied, but so it should be exactly the same. I never tried, but it should be exactly the same thing.
Okay, thank you. So, any further questions? Okay, so it's lunchtime. We'll be back at 2.